Welcome to the deep dive. Today we're plunging into some of the universe's most dramatic stuff. Not pretty nebulae, not sparkling galaxies, but, cosmic violence on a scale that's hard to even imagine.
Yeah, absolutely. We're looking at the ultimate heavyweights of space, black holes and neutron stars.
And specifically, what happens when these two incredibly extreme objects get tangled up?
Exactly. Our mission here for this deep dive is to really unpack that final destructive dance when they spiral together.
We want to get into the physics, the moment-by-moment breakdown.
And how scientists are using some pretty mind-bending tech to virtually see these things that are essentially invisible otherwise.
Right, and we're basing this on some fascinating new research, really detailed simulations coming out of places like Caltech.
Yeah, this work is shedding light on phenomena that honestly were mostly just theory until pretty recently.
Okay, so let's set the scene. This cosmic dance floor.
Right, so first off, remember, lots of stars aren't alone. They exist in pairs and binary systems orbiting each other.
But we're not talking about regular stars here, are we?
No, not always. The really traumatic pairs, the ones we're interested in today, they're what's left after stars die. The dense remnants.
So let's introduce the players. First up, black holes.
Okay. Ultra-dense leftovers from massive stars going supernova, immense gravity. And if two black holes collide, they just merge, make an even bigger one. Simple enough, relatively speaking.
Relatively. Okay, player two.
Neutron stars,
Mm-hmm.
also born from supernovae, but typically smaller, less massive than black holes, still incredibly dense, though.
So what happens when you get this pair, a black hole and a neutron star, orbiting each other?
Well, if they get close enough, and that's the key, the black hole's gravity usually wins out. Big time.
It just eats the neutron star.
Pretty much. Devours it completely. That's the general outcome we expect.
Okay, that sounds incredibly violent. But these new simulations, they're looking at the moments right before that happens, right? The final seconds.
Precisely. That's what's so remarkable. Researchers at Caltech, led by Elias Most, use supercomputers to model this in more detail than ever before. What happens just before the neutron star gets swallowed?
And what did they find? What was the surprise?
Get this. About 1 second before the merger, the neutron star's crust, its solid outer layer, it starts to crack apart. Massively.
Crack apart? Like how?
Most put it perfectly. He said it cracks just like the ground in an earthquake.
Wow.
And another author, Katerina Chatzianu, she added, it's like the neutron star breaks like an egg.
Breaks like an egg. That's quite an image for something so, astronomical. What's actually causing that fracturing?
It's the sheer gravitational force of the black hole.
Oh, yeah.
It's so intense nearby that it exerts different forces on different parts of the neutron star.
Yeah.
It basically shears the surface.
It pulls it apart.
Exactly. Opens up these huge rifts. And remember, neutron stars have ridiculously strong magnetic fields.
Okay.
So when that crust shatters, the magnetic field lines anchored to it get violently shaken. They wiggle around, as Most described it.
Like shaking strings.
Yeah, like strings attached to the neutron star being cracked like a whip. It creates this sort of cracking sound in the magnetic field, generating these magnetic ripples.
What kind of ripples?
They're called Alfvén waves, powerful disturbances traveling along those magnetic field lines, named after Hannes Alfvén, the Nobel laureate.
Right. Alfvén waves?
And these waves, they don't stay as ripples. They build up, transform into a blast wave.
And that produces something detectable.
Yes, that's the key prediction. It produces a burst of radio waves about a second before the neutron star is actually swallowed.
So you could potentially detect this cracking sound, as a radio signal.
That's the idea, specifically as a fast radio burst, an FRB.
An FRB 1 second before the collision. That's incredible, like a warning flare.
Exactly. And there are new telescopes being planned,
Yeah.
like the Deep Synoptic Array 2000, the DSA 2000 out in Nevada, that might actually have the sensitivity to pick these up in the future.
Okay, so that first simulation showed the crust cracking, the pre-quake, essentially. But there was a second simulation, too, wasn't there? Looking at what happens after the fracture.
Yes, led by Yoon-Soo Kim. This one looked at the moments, the milliseconds really, following that initial break as the black hole is closing in for the final gulp.
And what did that show? More fireworks?
Oh, yeah. Something even more powerful. Monster shock waves.
Monster shock waves. Seriously.
That's the term. They're predicted to be the most powerful shock waves in the entire universe, shooting out from the star.
And these were just theoretical before.
Pretty much. They were predicted recently by Andrei Belobrodov, who's also on this paper, but these simulations are the first to really show them forming in this scenario.
How do they form? How can we visualize that kind of power?
Gary used a great analogy. He said, it's like an ocean wave. You know, the ocean's quiet, then waves come ashore, they get steeper and steeper.
Until they break.
Exactly, until they break. He says, in our simulation, we can see the magnetic field waves break into a monster shock wave. It's just raw cosmic power unleashed.
Wow. So more waves, more signals.
That's right. These monster shock waves also convert their energy into blast waves, and these also produce radio signals, potentially even stronger ones.
Wait, so astronomers might detect not one, but two radio bursts.
Yes. One right after the other, all within that last second before the neutron star disappears into the black hole.
That's huge. Why is that so significant?
Well, it suggests that even if these mergers don't create a big, bright visual explosion like a kilonova, which we haven't definitively seen from a neutron star black hole merger, yet they could still produce these really strong radio signals.
So even if it looks dark visually, we could still hear it radio-wise.
Precisely. It gives us another way to potentially detect these events and study the physics happening right at the very end.
Okay, the story doesn't end when the neutron star gets swallowed, does it? The second simulation showed something else.
It did, something really exotic, actually. For a very brief moment after the neutron star is consumed, something they're calling a black hole pulsar might form.
A black hole pulsar. Okay, I know a regular pulsar is a spinning neutron star, like a lighthouse.
Exactly. A highly magnetized spinning neutron star beaming out radiation.
So a black hole pulsar is?
It's hypothetical, but the idea is the black hole itself, after swallowing the neutron star in its magnetic field, briefly mimics a pulsar. It launches these magnetic winds that sweep around as it spins.
But hold on, black holes eat things. How does it launch winds? And why would it have a magnetic field?
Good question. Most explains it like this. If the black hole eats up the neutron star, it's also eating up its magnetic field.
Okay.
And he says it needs to get rid of that. The black hole doesn't want the magnetic field, it repels it.
So it sort of spits it back out.
In a way. The simulation shows the black hole dragging this unwanted magnetic field around as it spins, and this process flings out plasma, creating these magnetic winds.
And they described a geometry for this?
Yeah, they mentioned a ballerina's skirt geometry.
Yeah.
Picture the magnetic field lines flaring out for the black hole's equator, dragging hot plasma along with them.
Like a spinning skirt.
Exactly. And where these fields interact, you get electric currents, heating up the plasma intensely.
And this black hole pulsar state, it lasts.
No, that's the thing. It's incredibly brief. The simulation suggests it lasts within seconds. Then the black hole just settles down and becomes quiet again.
Seconds. But even in that short time, could it produce a signal?
Potentially, yes. A short burst of high-energy photons, X-rays, or maybe gamma rays. Another fleeting signal to look for.
Okay, let's connect this to another way we detect these cosmic collisions. Gravitational waves.
Right, the ripples in space-time itself, predicted by Einstein. LIGO made that huge first detection back in 2015.
That was two black holes merging, wasn't it?
It was. And then, importantly, in 2017, LIGO and the Virgo detector in Europe caught two neutron stars colliding.
Ah, and that one was seen with light, right, the kilonova.
Yes. That event, GW170817, was a game changer. It produced gravitational waves and a massive electromagnetic signal. The kilonova explosion, which sprayed out heavy elements, things like gold and platinum, we saw it across the spectrum.
So we know neutron star mergers can make kilonovas. But the neutron star black hole ones, still a question mark.
Still a question mark on the bright kilonova front. We haven't seen a confirmed optical counterpart yet. But that's why these simulations predicting radio bursts, X-rays, or gamma rays right before and during the merger are so exciting.
It gives us something else to look for, even if there's no big visible flash.
Exactly. And this ties into the efforts of the gravitational wave detectors themselves.
How so?
Well, the LIGO team and others, they're constantly improving sensitivity. They're working toward detecting the gravitational waves from these mergers earlier and earlier.
How much earlier?
The goal is potentially up to a minute before the final collision actually happens.
A whole minute. That sounds like, well, not much time, but in astronomical terms.
It's absolutely crucial. As Caterina Cazziano put it, that minute gives astronomers precious time to get alerts, point their telescopes, radio, X-ray, optical, whatever, towards that patch of sky.
To try and catch those fleeting electromagnetic signals the simulations predict?
Precisely. She said, the gravitational waves are one piece of the puzzle, while the electromagnetic radiation is another. We want to put the puzzle pieces together.
Building that complete picture of these invisible events.
That's the goal. Multi-messenger astronomy. using both gravitational waves and light or other radiation.
Okay, let's talk about the how. What technology actually made these incredibly detailed simulations possible? You mentioned supercomputers.
Yes, but specifically supercomputers packed with GPUs, graphics processing units.
GPUs,
Yeah.
like in my gaming computer.
Fundamentally, yes.
Yeah.
The same kind of technology, just on a massive scale. The team used the Perlmutter supercomputer at Lawrence Berkeley National Lab.
Why were GPUs the key? What's different about simulating a neutron star hitting a black hole compared to, say, two black holes?
Well, as most explained, simulating two black holes merging mostly involves Einstein's general relativity. Complex, but relatively focused. But when you add a neutron star into the mix, suddenly you have a lot more physics taking place. You've got the incredibly complex nuclear physics inside the star itself, how that ultra-dense matter behaves.
Right, it's not just empty space warping.
Exactly. And you also have plasma dynamics, how the superheated gases and magnetic fields around the star behave under these extreme conditions. It's just much, much more complex computationally.
And GPUs are good at handling that kind of complexity.
They excel at it. They have this massive parallel processing power. They can do many, many calculations simultaneously. That's why they're great for graphics and also for AI, and it turns out, for simulating messy astrophysical events like this.
So was a computational bottleneck before.
Absolutely. Most mentioned they'd worked on similar simulations for about 2 years without GPUs, and they struggled. But when they got access to the GPU-powered supercomputer, he said, suddenly everything worked and matched our expectations.
Wow, so they just didn't have the raw power before.
That's what he implies. We simply did not have enough computing power before. It really highlights how advances in computing directly enabled advances in theoretical astrophysics.
And how long does one of these simulations actually take to run?
Even with the GPUs, they're pretty hefty. About 4 to 5 hours for one detailed run.
4 to 5 hours to simulate maybe the last second or two of a star's life before it meets a black hole. That's incredible dedication.
It really is. It's a testament to how computational science is letting us, peer into these cosmic laboratories where physics operates at its most extreme.
So let's wrap this up. We've journeyed through this incredible cosmic collision guided by these cutting-edge simulations.
Yeah, we've seen how scientists are now, in a way, seeing this previously unseen violence. From that initial quake, the cracking crust of the neutron star,
to those monster shock waves ripping outwards.
and even the potential fleeting birth of a black hole pulsar right after the neutron star is gone.
And it's all thanks to these incredibly powerful simulations run on supercomputers and the promise of observatories listening for those faint whispers, radio bursts, X-rays, gravitational waves.
It's truly amazing when you step back. These events, happening light years away, unfolding in less than a second.
Utterly cataclysmic.
Right. And yet we're starting to piece together what happens from these incredibly faint echoes, these whipples in space-time, and fleeting bursts of light.
It makes you wonder, doesn't it? What does it mean that we can actually reconstruct these incredibly intricate, violent moments just from those echoes?
Yeah, and it raises the question, what other sounds, what other signals is the universe making that we just haven't figured out how to hear or see yet?
As our technology keeps getting better, as our understanding evolves, what other secrets of the universe's most extreme physics are waiting to be uncovered? Something to think about.